This is NV Fitton here to talk about polynomials. This is an introduction to polynomials in general. The first of 3 anticipated videos on this subject. So as you can see, for this one we're going to have examples and we're going to define the idea and talk about one super important fact that has to do with all polynomials. So here we go. Here are some examples. Let's see, make that a little brighter. Examples of polynomials. They're functions, of course. This constant function is a polynomial. This linear function is a polynomial. Actually, it's a binomial because it has 2 terms in it. Here's a quadratic function. That could also be called a trinomial, but we'll generally think of it as a quadratic. Here is another polynomial. See anything that all of the exponents here have in common? Including the exponent right here and the exponent right here. You can see the x to the 0th there, can't you? All of these exponents are integers. With this one, I have organized them so that we have the largest integer first, and then we count down from whatever 3, 2, 1 to 0. Okay. And here's my last example in this series. I have the square root of 7 times x to the 4th. Why square root of 7? Well, basically because there isn't any law against it. Square root of 7 is a real number, so I'll use it if I feel like it. Here are some counterexamples, things that are not polynomials. Well, if I take that square root and I put it over the variable rather than just over a real number, I could rewrite this as 3 times x to the 1/2. 1/2 is not an allowable exponent for this. Here is a ratio of 2 polynomials. This is called a rational function, and it has very interesting properties that we're going to study soon enough. And while it has polynomials in it, it is not a polynomial itself. Here's another rational function. I might want to write this one as x minus 3 to the power negative 1. Now, because that power is not an integer in the set 0, 1, 2, 3, and so forth, that means that this is not a polynomial function. And these functions also do not share the simple properties of polynomial graphs that I want to mention right now. Graphs of polynomials are all very smooth and curvy, unless they're simply straight lines. But most of the ones that we're going to be interested in have this nice smooth curvy shape. They do not go like that in a cusp. They never have gaps. And notice also that this one goes on forever at both ends. That leads us to the next fundamental thing about polynomials, and that is that the domain of every polynomial is all reals. Okay, now that we have seen a few examples and counterexamples, let's get to the definition. Okay, so I'll call my function p of x for polynomial. So it has a lot of coefficients multiplying a lot of x's. And I'm numbering them all from the biggest to the smallest. And here we have x squared, which follows so many x cubed, x to the power 1, x to the power 0, right there. Okay, so all of these coefficients, a whatever, have to be real numbers, and the leading coefficient cannot be equal to 0. So this is called a polynomial of degree n. Okay, so n is the value of the largest exponent that we have in our polynomial. So if our polynomial is p of x is equal to 3x to the 4th minus x plus 5, this is a polynomial of degree 4. Okay, that's going to be important. Now, the big take-home fact from this introduction is this, that a polynomial of degree n is always the product of exactly n linear factors. So let's look at an example that is quite simple. Let's let our polynomial be x squared minus 5x plus 6. Well, we can see that it is a polynomial of degree 2 right there. And I chose this because we can easily factor this into x minus 3 times x minus 2. And we see that we have exactly 2 linear factors. Now, a linear factor. Linear here means that if we said something like y is equal to x minus 3 by itself, this would be the equation of a line. So a linear factor has the form ax plus b, as these guys do too. So x minus 3 times x minus 2, 2 linear factors. And let's look at another polynomial. F of x is equal to x cubed plus 5x squared minus 5x minus 10. Now I cooked this one up in advance. It's not something that I can just look at and factor by myself, but I do know for a certain fact that this one factors into x plus 5 times x plus 1 times x minus 2. So again, we have the degree 3 and 3 linear factors. So we are going to be focused a lot on factoring polynomials, but there's a lot of stuff to the factors of polynomials that you didn't get in your earlier study of algebra. And that's going to be our focus now in pre-calc. I believe that's the end of part 1.